did my undergrad studies in Portugal in physics, but I never really got to study like pure physics. I already for my master's here, I was working in using evolutionary game theory to study complex systems. And then I did my PhD at the Max Planck Institute for Evolutionary Biology. Also there were, like, I was in a theoretical group, not so much into the biology itself, but using like evolutionary game theory. So taking the evolutionary theory from there. And about a year ago, I moved here in Amsterdam. So more specifically at the Informatics Institute at a group called Pro-Social Dynamics Lab, inside another group which is called Socially Intelligent Artificial Systems. So in this group focus more on how AI can be pro-social and more fair. But also there we're using game theory to study these strategic interactions and how cooperation can emerge and be sustained in several systems. The project that I'll be presenting today was my last project of the PhD. So together with Christian, which was my supervisor, he's in Zoom last time I checked, and Fernando Santos, or Fernando P. Santos, because I guess there's other Fernando Santos in town. So he's leading this pro-social dynamics lab. Unfortunately, he's not here today. He's at Amos in the US this week. But yeah, this work is in collaboration with them. So as I said, I use in my work mathematical and computational models to study social behavior. And by social behavior, I generally mean that one's behavior will affect others and vice versa. So there's this interdependence that creates some interesting complex effects. And as I've been kind of hinting at, one such phenomena that emerges in social behavior is cooperation. We can define cooperation as simple as paying a cost for someone to receive a benefit. And there's all sorts of examples, both in nature and human societies, where cooperation is prevalent. So in some species, they emit alarm calls to let the group know that some predator might be around, but while giving this alarm, they also exposing themselves. So we see this as a cooperation act, but also in human societies, countries cooperate to produce, to create international agreements, for example, to protect the climate. So we can see cooperation at all levels. And it has attracted a lot of attention because it's both theoretically, empirically, an interesting problem. And what usually people use, or at least theory people that are using game theory to study this problem, they depart from this very simple game. So this is a payoff matrix, and we have two players. One player selects the column, the rows, and the other one selects the columns. And if one decides to cooperate, they pay a cost C. And if you are cooperate with, you receive a benefit B, which is higher than the cost. This is called the donation game, which is like a specific case of the prisoner's dilemma. And how the question would be, how do we solve this game? So what is the most likely outcome from this game? And if we think from the role player's perspective, no matter what our co-player does, it's always best for us to defect, because we don't pay the cost. If they cooperate, we get the benefit. If they don't cooperate, we get nothing, but at least we don't waste any cost. Now, if the other player thinks exactly the same, they will defect as well. And this would be the so-called Nash equilibrium of the game, because if both are defecting, none of these players would have an incentive to deviate from it. But now they get a payoff of 0, and they could have obtained some positive payoff or utility or reward if they had both cooperated. So this very simple game illustrates why cooperation is puzzling, because we're kind of saying that the rational or optimal decision is to defect. But if we had both cooperated, the utility would have been better for both of us. We can kind of extend these games to make them more general. And now we're kind of talking about social dilemmas in general, where we fix the mutual cooperation payoff to be 1 and the mutual defection payoff to be 0. So it's always better if you both cooperate as compared to both defecting. And then depending on the signs of these parameters A and B, we'll get other sorts of dilemmas, other games that might give you a prediction, which is not always only to defect. So we call this two-player social dilemmas. And because if we think that this very simple model is a good model to explain cooperation, well, it kind of doesn't really explain it, right? Because we would expect everyone to defect. And so people wanted to explain why we see cooperation, how it is emerging, and how it is sustained in all sorts of systems. So a variety of mechanisms were put forward to explain it, and there are several such mechanisms that would explain. We can think about kin selection, because you would cooperate towards your own kin if we're thinking about genetic relations. We can think of direct reciprocity. So if we play these kind of games over and over with the same partners, then to cooperate suddenly kind of is also a rational strategy, because then we expect the others to cooperate and we'll cooperate again tomorrow. So we extend this relation over time. When we're not meeting when we're not meeting the same partners every day, we could also rely on some sort of indirect reciprocity, where we rely on reputation. So I will cooperate so that I gain some good reputation, and even strangers would cooperate back. So there's even more mechanisms that could explain it. And there's also many models that would study these different mechanisms. So usually people use evolutionary game theory to study these mechanisms. And we can think of evolution of behavior in the genetic sense, but we can also think of a population that is learning, that its agents are learning over their lifetime. And the theory that we use, it's kind of similar. Either we're thinking about genetic evolution or learning over time. So we could also think that what is driving this change of strategies, or this adaptation of strategies, could be imitation, for example. In this case, we think of people are learning from others. So we think of social imitation. So if we perceive others as more successful, if someone that is very pro-socially successful, maybe I would be more likely to copy those strategies. So there are many models also out there. And what I want to pinpoint now is that something that is shared in common in many of these models is that at some point in the model, we have to define how players are updating their strategies. So let's think that we have an agent, and then at some point they have to decide whether to keep a strategy that gives them a payoff of pi, or to switch to something else. And let's assume that they're only considering one other alternative, which would be associated with a payoff of pi prime. And then they think, should I switch or not? And one such function that would define this decision. So this is the probability with which one would switch to another strategy, is this Fermi function, or sigmoid. This is widely used in the literature. That there are other functions, but this one is widely used. And what is also there is this parameter. So this switching probability depends on the payoff difference, but also on this parameter, which we call, in the literature, it's called selection strength. So this scales the difference in these payoffs. So the effect that this has in the switching probability function is the following. If we have, so now plotting the switching probability over the payoff difference, is if beta is very small, players will have very noisy or random decisions, and they will switch close to 50% chance. So this is close to a completely random process. If we increase beta, we'll now see that if the payoff difference is positive, they will more likely adopt what is the higher payoff strategy. But not always. There's still some probability with which they will go for a lower payoff strategy. If we make this very, very big, this function approaches the step function, and as soon as there is some advantage in the alternative strategy, they will most likely adopt it with 100% probability. So this beta has been related to, we can call it if efficiency in the learning process, as we think that more efficient learning will be like I can distinguish better the strategies that provide me a better payoff. We can also think of rationality, though rationality sometimes is also defined as much more than this, and would also imply some sort of, by being rational, I also assume that you are rational and you know that I am rational. So rationality is a bit broader, but we can also think that a more rational player would maybe be more inclined to or more efficiently adopt higher payoff strategies. We can also think that it's kind of a way to include noise in this decision making. But either way, what usually happens in these previous models is that this parameter beta is a fixed parameter, and it's equal for all individuals that are interacting. So everyone has kind of the same strategy update rule, and they have the same efficiency in the way they learn. So what we wanted to do in this project is to ask two related questions. One is if more effective learners, so learners that would have a higher beta, would they always be better than their opponents? And two, and more excitingly, if we let this selection strength parameter beta itself evolve, if it would evolve towards higher values. Yes.
In like status beta is like inverse temperature,
yeah.
Right? So it's and then the difference in the payouts, pi prime minus pi is like a Hamiltonian or something.
Yeah, so
like an energy function.
Yeah,
so do people also consider other energy functions except linear? So linear in the payout. This is linear in the difference of the payouts, but
so non-linear
quadratics or some non-linear stuff. Does that have a big effect? Or...
Definitely, I've seen other functions which are different from this sigmoid function, but they would still be linear in this difference. I'm not sure if I've ever seen something which is not linear on this payoff difference, but what I know is that people use this one a lot. But that's a good point. But even when they're not using exactly this function, there's still some sort of parameter that is equivalent to this selection, like how much players are distinguishing this payoff matrix. Like, yeah. I think this was inspired in physics, the function. Okay, are these questions clear? And like also like the naive expectation would be that if I am using a learning rule that provides me, yes, that's also the case. Yeah. That there's interesting relations to the Boltzmann rule. Yeah. So the naive expectation would be that okay, if I am adopting more often the higher payoff strategy, maybe this should be evolutionary advantage to see beta increase. Okay, so to study this, we have a model that will be composed of two big parts, one short-run dynamics and one long-run dynamics. I will first focus only on the short-run dynamics, which we model using introspection dynamics. And in this short-run part, what we're doing is fixing the selection strengths for now. And players will be learning their strategies over time. for a given fixed selection strength. So now they're only learning whether to cooperate or to defect, and beta is fixed. So let's think of a two-player game. They can have potentially different betas, and the way that they will learn how to play this game is we start in a given outcome or state. So both start by cooperating. And then on a next step, we choose one of these players to consider an alternative strategy. So in this case, we're only working with two strategies. So they think, what would I obtain if I had played defect instead? So they would get a payoff of 1 minus A. So they do this comparison using the Fermi rule, and they will switch to D with the given probability, well, given by this Fermi rule. And we keep doing this over and over. And so we can track how often these players are in one of these 4 outcomes, and then see what is the average frequency of each of these outcomes, which are only 4 for this game. So putting some math into this, this process that I just described is a Markov chain. So we can, and because there's some noise in how players are adopting their strategies, considering that beta is finite. So it's not a step function. So there's always a chance that you choose a suboptimal strategy. We can derive a unique stationary distribution. So basically the frequency of each of these states in the long run. So this is the stationary distribution. So likelihood of each of the outcomes or states. And just to show you how simple this can look like, if the two players have the same beta, the stationary distribution looks as simple as this. So you see that if you substitute beta by 0, it's the completely random scenario. So it's the uniform distribution over all 4 states. So 1/4 probability with playing each of these states. What we can do with this also is to calculate the average payoff of a player that has beta 1 against a player with beta 2. So for that, we just calculate the mean payoff. So multiplying the frequency of each outcome with the respective payoff of that outcome. And now, for example, if we're looking at asymmetric betas, the payoff that a player with beta 1 against a player with beta 2, it can be written explicitly with this form. The details don't really matter. It's just to show you that we can now work with this expression. And this is how we define an average payoff of this game. So now I can show you the results for this short run part of the model. So I'll be showing the stationary distribution over a couple of games with symmetric and asymmetric betas. So far, so good. And so first, for the prisoner's dilemma, remember that the Nash equilibrium of this game is to mutually defect, is like the stricter kind of dilemma. And if we now plot the stationary distribution of a game where players have the same beta and kind of relatively low beta, we see that they're mostly defecting with around 50% chance, but they're still also doing a lot of the suboptimal outcomes. Now, if we increase beta, we see that they're now much more playing mutual defect. So this is approaching the Nash. As we increase beta, it's approaching the only Nash of this game. But now, if we introduce this asymmetry in betas, what we see is that the higher beta player, the most efficient at recognizing this higher payoff strategy, which is D, is defecting much more than the other. So what happens is now that these, I don't know if you can see the numbers here, but here is the average payoff of each player. Now the higher beta player has much higher payoff than the low beta player. So they're defecting much more, so they can exploit this player a lot. So if we now plot this super game where we think that the strategies or the two options that agents have is these two different betas, if they have some control of how would they learn, and have these average payoffs here. So these payoffs are coming from these average payoffs. We see that the higher beta dominates over the lower beta. So it's always best to have higher beta, more efficient learning. So this is kind of expected, but let's look at another game. Yeah, this all clear how this matrices function. Okay, so now if you look at the Snowdrift game, which is a game that has now two Nash equilibrium, so to cooperate and to defect. If we look at the symmetric low-low case, we see that players are mostly in the Nash equilibrium. If we increase beta further, we see that these states gain again more weight. So it's again approaching the two Nash equilibria of this game. But now when we have an asymmetric situation, suddenly the high beta player is not having a higher payoff than the other. And what's happening here is that the low beta player is adopting more often what is the suboptimal thing. By doing this, the higher beta player, which is more responsive, more rational, and it will more rapidly drive the game back to a good equilibria, they will end up in their least preferred equilibria. So basically, if we think that we're departing from one of these good outcomes, and suddenly one is deviating from these good outcomes more often, and then the higher payoff the higher beta player will be more reactive to that. They will end up being much more often in this outcome here, which is their least preferred. So 0.1 as opposed to 1.5. So by being more erratic, it's kind of I am the low rational player in the immediate time is kind of foregoing some good outcome, and the other immediately responds, and then they end up being in the preferred outcome of the low rational player.
Wait, can I ask one thing?
Yeah.
So here there's a Nash equilibrium if one cooperates and the other one defects?
Yes.
Or the other way around? But what does it mean for the population?
It would mean, if you think of a population, it would mean that the fixed point would be a coexistence of cooperation and defection. So the two Nash is one cooperates, the other defects. So if you think of a population,
you don't know what the other will do, right? So you will always.
No.
So how does it get that you never get cooperate?
You do a little bit, but very little, because that's a suboptimal outcome compared to the two that are not the two that are Nash.
Maybe I'm thinking about it the wrong way. But
maybe don't think about a population yet, but just how two players would reason by playing this game. And so if they are both, if they're both being very efficient at finding a good strategy, they will most likely be in one of these outcomes. But if now one is making more mistakes and going to some suboptimal state, the other responds much faster because has a higher beta, and then they end up in their actually a less good, because these are two Nash, but one is better for one and one is better for the other.
So you know what the other does before you make your decision.
When you're updating your strategy, you kind of assume that, okay, if I had done something else, provided that the other one is fixed, would that make me better or not? So in a way, when you're doing this strategy update, you kind of assume that the other is fixed. Kind of the same idea as Nash. So the Nash equilibrium would be, you would think that, okay, if everyone else is doing this, if I change, would I gain an advantage or not? And if don't, then that's a Nash equilibrium.
So maybe I missed it, but these values in the opposite? You computed them by doing a numerical experiment.
No, actually, you can calculate them by calculating the exact value of the stationary distribution.
These
So,
are exact values.
yeah.
Okay, so then the next question is, are these values, are they surprising to you, or is this just something that you could have, reasoned that this should be the case before you did the computation?
They're not surprising because we proved in a previous work that, for example, if you in the limit when beta is infinite, this will tend to one of the Nash. That's why, like when here we increase beta, you see that the Nash equilibria have more weights. But then when there's a lot of noise or less than rational behaviors, other states are also possible. So you see, I don't know if you see my cursor here,
Yes,
but yeah, it's kind of the difference between this and that. But yeah, if you make it infinite, it will converge to a Nash equilibrium. We did this for 2-player games.
The surprising thing here maybe is that the more rational player gets trapped in the Nash equilibrium that's not beneficial.
Exactly. So now if we plot the super game again, we see that low beta is the one that dominates. So then you would see that, okay, it's actually advantages not to be the smarter player.
It gets trapped to the other equilibrium because the other one makes some mistakes every time.
Yeah. You'll see that this doesn't happen for all Snowdrift games. So this game has to hold some conditions have to hold, as in like one player is more likely to do a certain kind of mistake, and then the other will correct this mistake and will end up being in the least preferred. It could be the opposite. So it kind of depends on, but I'll show that a bit later. But I don't know if there's evolutionary biologists in the room. So this kind of we kind of related this finding with the Red King effect, where like when you have some sort of mutualism relationship, if you are the one that evolves slower, you can actually get an advantage from that, because then you will kind of commit to the same kind of behavior, and the other species that is co-evolving with this species kind of is more reactive, evolves faster, and then they also end up in their least preferred situation in this mutualism relationship.
Oh yeah, that's nice. I get that. I just miss maybe how is one game played? So you do know the other strategy. Otherwise, I can see that if you all the facts, then it will work.
But then all like players will be co-learning at the same time. So if I switch and on the next time, it can be that the other also switches.
So it's not that half of the population defects and half cooperates.
It depends on these parameters, but you will have like a fixed point in them, like where you have some fraction of players cooperating, some fraction of defectors in the population. But let's maybe not think about populations yet, but maybe we can talk about that at the end.
The switching is you compute the expected pay that you get, assuming that your opponent does not switch.
So when we're doing when we're doing just one step of this process, we're assuming that the other stays fixed. So I compare 1 with 1 minus A.
Yeah.
But then on the next step, it might be that we're now choosing the other player to update. And then we just track how often they are in each state. So it's a way of learning this game, which
you're updating player by player, not both at the same time.
Not both at the same time, a random one at each time.
Yeah.
It can be any of them. But if you want this kind of, as I was saying, kind of is equivalent to Nash when we think of beta very, very high. Okay, so this was that. And let's now look at the staghand game. So in this case, the Nash equilibrium is to coordinate on the same action, so to cooperate and or to defect. In the low symmetric case, we see that they're mostly defecting. So now we actually don't see as before, that they go to the Nash with the same frequency, because in this stagnant, this is actually to defect is the risk dominant strategy. So if you know nothing of what your co-player is doing, so if you're assuming that they will either cooperate or defect with the same probability, it's actually better for the role player to defect, because the expected payoff is higher. So in this case, this introspection learning process selects the risk dominant strategy, and they're mostly defecting here and not actually taking this CC state, which is even a Nash. And if we increase, that's even more pronounced. And now what we see when we have, again, this asymmetry is that the player, again, with higher beta defects more than the other. And again, the other, by cooperating more instead, then again, the high beta player can also kind of react and be more in CC, because CC is a good state for both of them. So now the difference is that they can actually coordinate more easily in CC by one of the players doing more mistakes or having a noisier behavior. So now they are both better off here because they're defecting less and cooperating more, which is the best of the Nash equilibria for both of them. So if we look at the super game, we now see some anti-coordination situations. So the best that the two players can do is to have an asymmetric beta. So one player being more noisy and the other player being more reactive to that, because that makes them coordinate better in the good collective outcome, which is to mutually cooperate. Okay, so what we've seen so far is question number one, if more effective learners do better than their opponents, and we've just seen that depending on the game and also on these betas that we're comparing like pairwise, I was only comparing two betas at each time. We see that the answer is no. And now what we really wanted to do is to, okay, let's just let this selection strength evolve and see where it goes to. And already what we've seen so far kind of give us an intuition of what may happen. Okay, so this was the short run dynamics of the model. I will now explain what happens in the long run. And now we're going to use adaptive dynamics to model the evolution of selection strength. So this is a framework to study the evolution of continuous traits. So remember that beta can take any non-negative value. So we'll be using this framework. And now, to model the evolution of selection strengths in a population. So now I'm actually thinking of a population, large population, and players will have their beta. So this is an individual trait of each individual. And then the question is, if we have now a rare mutant with a different beta, will they, so if we have mutant Y in a population resident, in a resident population X, will they be able to invade this population, fixate or not? And we'll be defining the advantage or the fitness of these players by assuming that they meet all other agents in the population, and they get an average payoff, which is given by all the framework that I've just described. Is this clear?
They meet all others, you said? The mutant has a meeting with all others and then it gets an average payoff.
It will meet all others when we do the analytical derivation. It will meet a few of them when we do simulations.
Okay.
So I will start by explaining, so I just said we'll do simulations, but also some analytical derivations. I'll explain first how the simulations work. So we start with some large population. At each time step, we choose two of these individuals. In this case, they have different values of beta. And then, so in the simulation, as to make it simpler, they will meet each of them 3 other random individuals in this population, and they will derive an average payoff by interacting with these three individuals. So they have this average payoff, and now we need to decide which one of them dies and which one will reproduce. And this is based on the fitness difference, which is basically the average payoff that we get from here. So let's say that Y dies and X will reproduce. Now X will reproduce exact copy of themselves with 1 minus mu probability, and with mu probability, which is the mutation rate, we'll consider it to be very small. They will have an offspring which has trait uniformly distributed around their own. And this is also like a small value, so it's very close to the parent. And then we do this over and over, and we see what values of this beta evolve. Okay, let's see first what happens for the prisoner's dilemma. So now we have the value of beta here over time. This is exactly the same game as before. And we see that beta is increasing forever. So this was what we expected from what we've seen before. If you remember, the higher betas were dominating, at least one higher beta that we selected for the analysis before was dominating the lower beta. So beta always goes to higher values. For the snow drift, remember that we've seen that not always the higher beta was dominating. So what we see is that initially there's some increase. So they move from being completely random learners. So they actually evolve some efficiency in this learning, which makes sense. That is making them select good strategies, but at some point is no longer advantageous to increase these beta. So yeah, so we find this stable point where, okay, by having higher beta will not make me better off. Yes.
Question about the both plots. What explains the two linear regimes on the left? Is it something to do with the population size and time, or
this?
You have the inflection point, and then also why does it kind of level off at it's 10 to the my guess is not so strong. 10 to the 4 time.
This the 10 to the 8.
Why is it?
So it's so each time point is one of these iterations of the simulation that I've just explained. Is one pair. It's not like a generation, or is one
this
pair.
will change if population size changes.
Yes. If population is larger, this will take much longer. So it just chose the smallest population that would allow us to see some of this convergence, and then what will come next. Why this is linear, is that what you're?
Well, there's two linear regimes, I think, right? So something happens also around 5 to the 10 to the 7, I guess.
I think there's nothing about time, nothing special about when exactly things happen, because this will depend on the.
It's just on the population.
Yeah.
Plotting the average beta about the whole population?
No, so actually each of these points, it's one individual, is one person in the population. So there it's
one run then?
It's one run. So this is not this is not average over population, is over simulation, is one simulation, and each of these points is one agent. So there is some thickness in it because we're introducing this mutation around the parents. There's always some there's always some, they're all in the same interval kind of.
And that becomes constant as well. That variance becomes constant, I guess, defined by the mutation rate, because it becomes stable, I guess.
Yes, so I would say that from here, what explains this variance has to do with also how far you're from the parent, which was about 0.2.
Okay. So what I'm surprised here, so I would believe that if you show this plot and say these are all the new species that I introduced that have this increasing beta, that would make sense. But now this means that the old species with a low value of beta go extinct very quickly on this timescale of your plot, or
They go extinct. I wouldn't say they
Because the variance
quickly.
is small, you mean.
yeah, and you would
Yeah.
expect that at some point you would just see, like, you have something like 10 to the power 4 individuals. I mean, you would expect that there would be, you know,
Some
a
like,
small group that
Yeah.
would be increasing, and there would
Yeah.
be a large blob that just remains, because you're just constantly
Yeah,
choosing two individuals, you know, choose one and then go on. So you would expect that there would be some sort of lag in before the whole community. So maybe it's just a matter of time scales, but yeah.
you're plugging every single person in the population here, it's not like a.
yes. So all individuals are there. I'm not exactly plotting each point in time because I don't even need them because they're so close.
But it just means that per time step that you plot, so you plot every so many time steps.
Yes.
It means that a lot of speciation events happen in every time step that you plot. Otherwise, you would see some sort of a lag, or
Just everyone evolves, I think, right?
yeah, so everyone in the population
Or is
has
replaced.
evolved.
No, sorry. So we start. So when we start with all zero. So
Yes.
they're all zero. So as soon as we have something that is above zero, then they will start gaining some advantage.
Yeah.
And actually, also the mutation rate is very small. So for a while, what's happening is there is no mutation, but because there's this birth and death process, the mutant that is above zero, it's growing.
Yes.
Way before a new mutant is introduced.
How is it possible that?
So yeah, they're reproducing their own copy of themselves, so they're growing, but there's not exactly a new mutant so often. So
But
if we think
the
that
only-
mutant is a new value of beta, that is rare compared to how long this so for a long time they're just reproducing their exact copy. So
Yes.
as soon as
So you eliminate everyone before the mutation.
yes, you can there's total or like almost completely separation of time scales.
Okay, yes.
Yeah.
The only thing that really drives that is the opportunity driven by the mutation, and that's much slower
Yeah.
than the.
Exactly. Yeah. Okay. And now for the second, if you remember what we were seeing with one of these cases is that they would rather meet someone that would be different from them. So if you're high beta, you would rather meet low beta and the other way around. So at some point, so here you can actually see that I'm not plotting every single time step. So there is now some separation here, but they're initially increasing beta, and at some point there's a branching event. So now actually, because it's beneficial to have an asymmetry, there is a subpopulation that has lower beta and a subpopulation that has higher beta, and they are coexisting. At the same time, we can also see what happens in cooperation in terms of average cooperation. So we see that for Prisoner's Dilemma, this is going down because beta is increasing. They're being more they're defecting more. Also for Snowdrift, it decreases a little bit. It will never go down completely down because remember that Snowdrift we have these two Nash, so it's some of them are still cooperating. For the Staghorn instead, there is some increase of cooperation because remember what was happening when we have an asymmetry in the betas is that they're coordinating much more often in the cooperative Nash equilibria. So this is actually increasing from the branching point. Okay, we're doing bad in time. Okay, so what we can also do, so now I've shown you three different simulations for 3 different games. And we also wanted to know if we can actually derive these points analytically and their stability. So actually these dashed lines correspond to the analytical prediction. So we can predict the singular points or the fixed points. And I can explain to you a little, like very fast, how that goes.
Is there a dashed line in the first figure as well, or?
No, because there is no fixed point here, so it will always grow. I can explain a bit fast how this goes, but basically it's using all the adaptive dynamics framework, which is really nice and neat. So for the analytical predictions, we're thinking of the limit of infinite populations, rare and small mutations. And the crucial quantity that we need to work with is called the invasion fitness, which is defined as this, and is basically saying what is the advantage in terms of average payoffs of a rare mutant Y in a resident population of X. So, and remember, so we're defining this as before. So remember this, only this term looks like this, so we can work with this equation. And what do we do with this? So if this quantity is negative, the mutant will go extinct, no selective advantage. And if this is positive, they can invade. So what we can do with this quantity is to plot for any pair X and Y, if a Y mutant would invade X. And these are called pairwise invisibility plots for the prisoner's dilemma. So we're plotting the shade area is when this quantity is positive. So what we see by plotting this is that for any pair of resident and mutant, all mutants that are above the resident will invade. So this is completely consistent with this. And by looking at this, we see that they will always increase. So all the part above the diagonal is shaded. So this would always increase. For the snowdrift, what we see is that initially mutants that are above the resident can invade up to some point. Then the opposite happens. Mutants from below are the ones that will invade. So we have this converging point, which is where we converge to. And besides that, this is stable because once we reach this point, no mutant from above or below can invade the resident population. So that's why this is stable. And we calculate its stability by looking at this point and seeing that this is stable on Y. And then for the stagnant, we see something similar. So a converging point, mutants from above start by invading, mutants from below invade after some point. And then when we reach that point, what we see is that it is no longer stable in terms of there is a shaded area above and below. So mutants from both sides can invade this, this point. And that's why we see the branching. And we can calculate, we can exactly calculate these points, and we can also exactly calculate their stability using the invasion fitness quantity, which is basically calculating when this gradient goes to zero. So these fixed points, we just need to solve this equation. I think I'll skip this part.
You could just take it.
Yeah, but we can also, okay.
We can go beyond.
I will move and I'll just tell you what this part is about, and then if you want to talk about it, we can talk about it later. So what I was going to say is that we know that once we reach this point is an evolutionary endpoint because this point is stable, so there's nothing much more to see there. But for the stagnant example, because it's not stable, there will be a branching point. We need to know more what happens after branching. So I will kind of take this and I could discuss how we can go further and see exactly where how these two branches evolve after the branching point. And you can do that by kind of extending the idea of this gradient, but now we need to define a gradient for the two branches and check if these branches reach some stable point or if there will be further branching because they are not stable. And you can do this using like standard adaptive dynamics tool.
Do you still have an analytical solution when there's two residents for the invasion?
You can find so you could find, so for example, in the example that I was showing, after branching, there is no longer like a fixed point. So the two branches will always evolve and not stabilize. But there are some cases, for example, this one, for another stagnant game, where the two branches will actually reach, converge to a point where the two gradients vanish. So this will mean that now we're reaching a point where this coalition or this pair of traits reach a fixed point. And what happens next is that they will not, one of them, so the one above, is not stable itself. So then there will be further branching on that branch, but not on the other one. So we can only see this behavior with this analytical part, because to see further branch, I would need very larger population in the simulations. So this is remember that this theory is based on the assumption that we have infinite population, so we'll have to have much larger population to see further branching. So in the simulations, we've only seen the other branching case that you've seen.
Yeah, but to draw this figure in the middle down, you need an analytical expression of the invasion fitness when there's two residents.
Yes,
right?
so for that, yeah, that is correct.
And you do have that in this case, yeah.
Yeah, so for that you need to have this.
Mhm.
So now this as x1, x2, y, the invasion fitness of a y mutant that comes in a resident population of traits x1 and x2. And for you to know how this population, the resident population looks like, because we're assuming this separation of time scales, you need to calculate it in the equilibria of this population. So when x1 or x2 have reached, the two of them have reached an equilibrium point, which is
You also have an analytical expression for that.
yes. So for that, you just need to see when their payoffs become the same. So then you get the proportion of x1 and x2 when they reach this equilibrium point, and then you insert a mutant there, and you see how this, by interacting with these two residents now, if they have an advantage or not. Okay, so now the point, because we have this nice way to calculate the fixed points and also their stability, so we can completely define for which games there will be each of these dynamical cases. So we've been looking at only 3 games, so the ones that have symbol here, but by looking into all or many A's and B's, we can look at what these games look like for each point. And now the results are the results from the analytical predictions. I'm not simulating for every single of these points. And this is the result for all games. So the white areas correspond to when we don't find any fixed points. So this beta is always growing. There's no solution for this equation of the gradient. And then the orange regions are the ones where we see there is some convergence to a stable point. And then the purple ones are the branching situations. So what we kind of see from here, one is that not all staghans and not all snowdrifts lead to this interesting effect. We can explain why. So for the staghans, and maybe you already guess why, only the ones that are purpled are the ones where the defect is the risk dominant strategy. So for staghans, where actually to coordinate on cooperation is the risk dominant strategy, there is no this effect of, okay, we're already coordinating nicely in CC, So there is no advantage of this asymmetric beta situation. So you only see that for seconds where to defect is the risk dominant. It's usually, these are the kind of games that are more interesting when people are studying these social dilemmas, are the ones where to defect, it's kind of at odds with the other equilibrium of cooperating. Then the snowdrift, I kind of already explained. We need to, the games for which this happens need to fulfill hold these conditions where if the low beta player is doing this certain kind of mistakes and then the other responds, and by being on the least preferred outcome, then they are not better off. So these are the games that for which these conditions hold are those. And then what was more surprising for us is that even for some prisoners' dilemmas, we were seeing that beta evolving to a finite value still can happen. And this is for games where the absolute value of A is very small, and this means that the temptation to defect is very small. So actually, for these games like weaker prisoners' dilemmas, we can even see some advantage of having a less efficient way of learning the games. And we also explored some multiplayer games, which becomes a bit more complicated because now the average payoffs are more complicated to derive. But at least for some of these, which are like extensions of the two-player prisoners dilemma, two-player snowdrift, and two-player stagnant, for three-player games, which is the simplest one, which is not n equal 2, we kind of see the same picture, but there's now, with multiplayer games, there's way more ways of thinking of parameterizing a game. Okay, so as a summary, one thing is that the more effective learner does not always obtain the higher overall payoff. We see that boundedly rational learning can evolve and even heterogeneous populations. And then future directions can be many. So we could think that we could think of more complex games who are only looking at very simple games, two actions, 2 players. We also assume that in the long run dynamics, everyone could possibly meet any other. We could also think of structured populations. And I think this is also a very nice framework to study other possible evolving traits. So the evolution of learning more general, so evolution of social preferences, and so on. Yeah, thank you so much.
So if you go back to these pulse rates, right, of the increasing betas. So or what do you think is
The simulations.
And the simulations, yeah. So what you assumed here, this is essential for doing this kind of heterodynamics computation, that you are always in equilibrium. So you introduce your new mutant, and then the whole system goes to equilibrium, what confused me in the beginning.
So for the simulations, we just need to make sure that the mutation is sufficiently rare.
So I was wondering, how do you, and of course, if you want to use it as a dynamics computation framework, analytical framework, you need to have this equilibrium. But
yes,
I was just wondering if you can run these simulations out of equilibrium.
Yeah. So
will that change a lot in your conclusions?
So for the analytical framework, it is also an assumption in adaptive dynamics that when a mutant comes in, you're already in some ecological equilibrium, as they call it. In the simulations, you just need to make sure that your mutation is sufficiently small. And so if it is not, or if the population is too small, what you can see, for example, in the branching case, is that there is some initial branch, and then it can be reverted, because then if as the population becomes smaller and there is more mutation, then there's way more stochastic stuff going on, and then the branch gets reverted. So it never really kicks off completely. So to see this exactly, you need to make sure population is sufficiently bigger. Actually, for this one, I used 20,000, and for these ones, I used 10,000, and that the mutation is small, and also the selection itself, because now there's kind of another sort of selection, which is the selection, the long run selection. So when we're doing the birth-death event, this also has to be sufficiently strong. So like low stochasticity when we're choosing death birth. But yeah, so basically the simulations will be consistent with the analysis if we approach the assumptions of the analysis.
So after you introduce the mutation, you wait till the system becomes goes to stable equilibrium, and then you introduce another mutation, or?
I don't
And is it the type?
explicitly wait that the system reaches an equilibrium. I just make sure that the mutation is sufficiently rare as to let's start, I don't remember exactly how I've done, but there was, as I was saying, there was some cases if the mutation is not sufficiently rare, we wouldn't exactly see this. So I guess as soon as we've seen this, we know that, okay, the mutation is sufficiently rare as to be consistent with the analysis. Does this answer you?
Yeah. And I was wondering, the times that you plot, are those yeah, to me it's different, the evolution time, so to say, or?
Yeah. So in
like you introduce the mutation, you see where it goes, and then you plot the population at that time, and then you introduce another mutation. Is it that way, or is it?
Oops. That's my mom, by the way. Let's share PowerPoint again. Sorry, Mom. Continue to share. So you mean these points, these time points?
Yeah. What are those time points?
These time points. So for one time step is one round of this thing. So we choose two. There's a birth. There's a birth and death event, and that's 1 point of the simulation time. But again, I'm not showing, yeah, because this is really long. This is like very high, right? 10 to the 8. It's they're very long simulations. I think there's
just another technical question related to this. So you choose 2, and then you choose another 3 to
yes,
do the average payoff, and then birth and death.
yeah. I think there's a question on Zoom.
Yeah, I have a question. So perhaps I'm taking the analogy of beta to temperature too literal here, but this prisoner's dilemma plot here, for example, it looks a lot to me like simulated annealing, where you say, okay, we're going to optimize by lowering the temperature over time. So that at first we're still exploring a lot of options, and then as we lower the temperature, we're sort of settling in a better and better.
Yeah.
And then this bifurcation in the stack hunt. So there's another way you can use temperature to optimize functions, which is this parallel tempering, where you keep sort of different temperatures alive at the same time, and you allow some interactions between them. Is there a precise sense in which these are very analogous to these different optimization methods for sort of outside of evolutionary game theory, where you just say we're optimizing some functions with different optimization schemes, or is that a very superficial analogy only?
I would say that generally, when we're thinking of game theory, if you think of optimizing, it's always hard to think of you're optimizing something collectively, because what this is really what you're really optimizing is your own payoffs, and that can lead to a non-optimal thing for the collective. So you could think of, yes, that you're optimizing something, but it's like different learners are optimizing differently according to their own interests, and sometimes they're not aligned. So I think you can think of optimizing things in this way, but not so much when you have one single like reward function or function that you want to optimize, because then these agents here can have different of those functions.
Right.
If this answers.
I also have one question. So I see that in the Snowdrift game, you go to an average because it's good not to adapt too quickly, because then you are adapting too much to the other.
Mm-hmm.
So apparently this also works in a population sense. But then
Yes.
I was wondering, is it then so that the subpopulation that adapts slowly, so with the lower, oh no, that's in the second game then. But is it so that the subpopulation with the lower one is smaller? No, if I look at your thing, maybe it's not the case. I think is there a small population that
it's so
the others
in this case there are more the subpopulation that has lower beta, so this one is larger.
I'm just wondering how it works in a population sense that you.
But you mean what exactly do you mean how it works in the?
No, the idea that you said with the call in the Snowdrift game, it's good not to adapt too well, because then you adapt more to the equilibrium that's better for the other one, right? But in a population,
So here there's also another thing. So these they are also kind of, the two subpopulations are also self-interacting.
Yeah.
So this is what kind of, I think, drives the different proportions. So these the higher beta population, when they interact among themselves, they are way worse than well, actually no. When they meet the opposite, that's when they're will have their best outcome, because if we compare with so you will have all this so this the proportion of the two branches has to do with the balance that sometimes they will be meeting the opposite kind. Sometimes they will be the same kind, and on average they have the same payoff at equilibrium.
Just a more general question, because I missed the beginning of it. What I've seen, you get this quite theoretical, but do you have an application in mind? Because I'm just wondering about this timescale separation. Because it's the relation between the interaction frequency and this mutation. So whether you're going to look at, because I now realize that you're in Fernando's group, so you're in the same institute.
I think
so for the ecology case, I can clearly understand it, but if it's more a social process.
So one thing that we immediately related with, and that was the inspiration of this work, has to do with the literature in economics on bounded rationality. And there, what people usually say is that we have cognitive constraints, we have limited information, we have limited time, so we'll more often use some sort of heuristics, so we'll have some bounded cognitive way of dealing with these decision-making processes. I guess what we show here is that even if we think that you could completely, in principle, you can completely distinguish these strategies, if you're in a setting, in a game setting where there is a social dilemma, this could even be strategic. So it's not only about being bounded because I cannot infinitely compute what's the optimal strategy. It can be that it's actually strategic to not appear as the more rational player. So that is one thing. Of course, that the cognitive constraints are there, but what we're kind of saying is that even if they wouldn't be there, it can be actually strategic not to compute the optimal thing, or at least in the short term or in the immediate. It's you can see that maybe having lower beta is what is rational in the long term, in a way. And the other maybe application is that, in a way, we also think of what's lacking in many of these models is asymmetry in the way that people learn. So in the previous models, everyone updates the same kind of way and learns the same way. What we could maybe think in these new systems where we have different agents that maybe learning in different ways and in asymmetric ways, what happens if we assume some sort of learning mechanism for one and another different kind of learning for other. If we think of hybrid systems where you have a machine learning very differently than a human, so this asymmetric learning way of thinking, of course, that this is very far from being very realistic yet, but already kind of hints at this asymmetric learning.
So would you then, so going back to this timescale thing and the bounded rationality question, so if you try and do something along these lines with the L for all problem, or
with
the L for all problem, so just looking at how many instances, I don't know if you know, it's the same as the minority game more or less. You're looking at how many instances in history you're using of your outcomes. So it's not just instantaneous learning, there's a memory effect. And then this memory is going to have a kind of clear relation, I think, with your mutation and timescale. And then the bounded rationality and the timescales might be an interesting.
Yeah, I know that. So there are a lot of work in repeated games where the memory that you have, that is like how many past rounds you remember from your interaction, play a role. And actually, it has been shown that having a lower memory also is not always a bad thing.
Yeah.
So in a way, it could also relate to that, but it's actually it's a very different model, and I don't know if so they seem to be hinting at the same thing, but perhaps in very very different things are at play there. But yeah, okay. It's a good point.
Okay, there is one more question in Zoom.
Okay.
Can you please turn yeah.
Hi, can you hear me?
Yep.
So I was interested in interpreting beta more like attention. So it's like how much you care about the game. So if I really don't mind doing the dishes with my roommate, for me beta would be 0. So here you mentioned that in the case where there's a bifurcation in the stag hunt game, that when the players with high beta meet the ones with the low beta, that's when they really get the payoff. So is one interpretation of this like the population starts off and then some people really don't care about choosing either way, and then they are, if enough of them exist, they are able to cooperate amongst themselves and get some reward. But then there are this small group of high beta individuals who are really selfish, and they are really dependent upon this large population of low beta players. Is it right?
Let me think a little bit. So I think what you're saying, that you could interpret beta as if it is small, you don't care so much about the payoffs, and that has an impact of how then you will play the game. But the way that we then use the average payoffs as a proxy of fitness, we use the actual payoffs. So you could be learning using you could be learning being very slack off, or like being very little mindless of being very not very minding the payoffs. But then what gives you the fitness is the actual payoffs. So I guess what you're saying is that maybe in
like the high beta individuals, are they kind of dependent on this other branch?
Yes, in a way they are, yes.
Okay, thanks.
And if we only have so in this case that I'm actually showing right now, in this case, still the high beta player has the higher payoff. In the population, they will on average have the same payoff because these ones will still be meeting of the ones of the same kind. So they will actually have a lower payoff when they meet the other smart guys. But it's interesting when we think of only like two-player situation that you would be exploiting that in a way.
Okay, if there are no more questions, then let's thanks the speaker.
Thank you.